Alright guys, I have to be gone for Monday and Tuesday of this week, so I'm going to run you guys through a little bit of content here, and we're going to push your particle presentations back until Wednesday. You're going to need, hopefully you have the cart by now. If you don't have the cart, it's cart D, and you each should be watching this individually with headphones if you want, or you guys can all watch it together, but the projector won't be in the room. So anyways, I wanted to clear up something about comparing the four forces and set you guys to work on a project with that. So we're going to ignore the weak force for a while because it's really, really weird, but we'll bring it back in at the end. I want to talk to you guys today about gravity, the Coulomb force, and the strong force. And remember, we're going to Fermilab next Friday, so this is going to be a fantastic lead up here. So this is a friend. You know who this is? We've seen him before. This is helium. And you can tell because it has two protons, the blue ones, two neutrons, and then two electrons zipping around like idiots around the outside. This is obviously not to scale. You can tell here that I have it labeled here. This is 10 to the negative 15 meters. That's really, really, really small compared to the orbits of the electrons, which is like 10 to the negative 10 meters. So this is actually 100,000 times skinnier than this, which essentially maps out to something like having the thickness of a dime at the center of Kinnick, and you're up in the press box. So it's really, really, really small. And the problem with that is it means that the neutrons are really, really close together, but they're both positively charged. And we've talked about how that raises problems, and I'd like to address that problem. So the central question I'm going to ask today is, what is the force between these two protons? Should they be able to stick together? And the model of physics back in the early 1800s or late 1800s said, no, they absolutely shouldn't stick together. So there's something, something new, some new physics had to be discovered. And we've talked about how that's the strong force, but we're going to get into that mathematically today. So here's some math, right? The question is, how are the protons repulsed from each other, and how are the electrons attracted to the nucleus? And the question is, or the answer is, some physics that looks astonishingly like gravity. You notice here we have a force, and then here you have some things on the top. This k is a constant. It's equal to 9 times 10 to the 9. These q's are a lot like the masses from the gravity law, but they're the charge of whatever it is that are pushing or pulling on each other. So in this case, this would be the charge of one of the protons, and this would be the charge of another one of the protons. And charges are measured in coulombs. And everything that has like a plus or a minus 1, that's what we call the elementary charge, and that's 1.9 times 10 to the negative 19 coulombs. You should probably just commit that to a stored variable in your calculator. That's what the STO button does. And then R on the bottom is the distance between the charges, just like gravity. So if you want to know the charge between the protons, you plug in this for Q, one for Q, the other one for Q. They'll have the same, they both have E because they're both plus 1. You'll plug in K, and you'll plug in that distance between them, that 10 to the negative 15, and you'll get out a force. And we're going to do that in a second. But just a little bit more on gravity and this Coulomb force. And why is it called the Coulomb force, right? Because obviously the dude who did these first experiments with like balloons and charging on hair, his name was Coulomb. And if you guys really want to, you could probably actually measure this K value. If you take a bunch of balloons and you can actually levitate one of them, you can figure out where Fc equals the force of gravity, and then you could solve for K. If you guys have some free time or you feel like doing that experiment, feel free to go nuts with that. So anyways, why does this Coulomb force look exactly like gravity? And the answer is because they pretty much come from the same mathematical idea, but they are absolutely not the same physics. So this picture right here is the crux of the idea. You have this source S, and in a Coulomb law, that source is a charge, like an electron. Right? An electron has negative 1 E, or negative 1.9 times 10 to the negative 19 coulombs. A proton has positive E. Or you could have a mass, right, like the Earth. That could be your point source. And as you move away from it, you can see how like the field lines, right, from the gravitational field or the electric field or whatever field, they spread out evenly so that if you're 1 r away, you've got this little tiny square where all these field lines pierce it. And that means the force field you feel is really strong. But if you move 2 r away, you end up with exactly 4 of those exact same areas. And so the force lines are spread out over 4 areas. And if you go 3r away, those force lines, or those field lines, are spread out over 9 boxes. And so you can see it's going like the perfect squares. So you end up with this r squared on the bottom, which is where that comes from. And because gravity and the Coulomb force from electric charges both behave this way, they end up with both having the exact same mass. And this is just a sort of awesome result of doing some calculus for figuring out what happens when you have a point source. It has nothing to do with the fact that they're the same. In fact, they're completely different forces. Gravity is embarrassingly small compared to the electric force. Another picture here that might help you out is that if you have something in the middle and you look at a surface of a sphere around it, right? If you like are just feeling a force from it, that area is going to be like r squared because it's a cone. So this is called solid angle or stare radians, if you want to Google that and dig into that a little more. So anyways, back to the problem at hand. What I'd like you guys to do now is stop the video and calculate these 4 things. Okay? So what is the Coulomb force, or the electric repulsion between the protons? And go ahead and use 10 to the negative 15 as your R. Second, what is the gravitational force between the protons? Now that's going to be attractive. And again, you'll have to Google the mass of the proton, which is a commonly known value. Do it in kilograms. 3, what is the Coulomb force between the electron and the nucleus? So you have this electron out here in this nucleus. Well, that's going to be attractive. And I would use half of this number if I were you, because this orbit is relatively big. And you'll have to Google, remember the electron has negative elementary charge, and the neutron, or the proton, has positive E. And then finally, what is the gravitational force between the electron and the nucleus? So what is the attractive force that's keeping these on here from gravity? And you'll have to Google again the mass of the electron and the mass of the proton in kilograms. The mass of the electron is really, really small. Something like to the negative 31 kilograms or something like that. Okay, so go ahead and pause the video right now. I'm going to flip to the answers, so go ahead and work these things out. Okay, so assuming you paused the video and actually did some math, here's the answers. And I'd like to just interpret these answers for a minute. In fact, I'd actually like you to, again, now that we have the answers up, pause the video and talk to people who are also ready to talk about this, who are done with the problems. And what does this mean? What does it mean that number 1, which is the electrical repulsion between them, is huge, but the gravitational attraction is so little for the protons? What does that mean? So stop the video and, sort of make some explanation about what that may mean. Okay, and then for the electron, you can see that both of these forces are teeny, 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 tiny. And when we get back, we're going to see if these forces can be added up to be a centripetal force to keep the electron in orbit. But mostly I'm interested in you guys analyzing these 2 answers, which I think are really, really interesting. This is really, really small, in case you didn't notice, and negative. And a point on the negativity, when a force is negative, it generally means that it's attractive. So this gravity is pulling the protons together this strong, or I guess this weakly, if you want to think about it. And the electricity between the electrostatic force between the electrons is this strong and attractive to the nucleus. Okay, so hopefully you guys have had a chance to chat that out. Obviously there's a problem here. If you're being repulsed with 325 and being attracted with effectively nothing, you've got a pretty serious problem in that every nucleus isn't going to be stable. They're going to fly apart because of the forces. So there must be another force balancing it. So back in the 50s, they posited that there should be a strong force. And so what I'd like you guys to do for the next couple of days is answer some of these questions. First, don't Google them first. Sort of just try and, put forth a guess so that you can have somewhere to work with when you're Googling. What should the F equation look like for the strong force? How should that look? It's got to balance out that electrostatic push. What's its range? I mean, why aren't, if it's so strong, why am I not attracted to every other proton on the planet? And finally, what kind of particles feel it? Do electrons? Do muons? Do lambdas? Compare it to your particle. And finally, I'd like you to add a WordPress post about this idea. So what are the motivations for the strong force? So this is something I'd like you to work on. In fact, here's the to-do list for while I'm gone. I'd like you to finish your exhibit, your zoo exhibit for your particle. We'll present on Wednesday, but I'd like you to write that out. I'd like you to present the reasoning for the strong force. So that previous slide, feel free to go back if you want that. And then second, I'd like you, this is a new post, I'd like you to make a comparison of the four forces. And if you Google comparison of the four forces and you go to the hyperphysics textbook that's online that people use quite a bit, it looks kind of like this. See if I can find it. Let's see, hyperphysics fundamental forces. Oh, you can't see what I'm Googling, sorry. But it'll come up, this link right here. So I Googled hyperphysics fundamental forces, and this is a really, really good resource right here, this slide. It take a while to dig into that, but what I'd like you to do with that is make a comparison of the four forces. So just like I compared the size of Kinnick to the size of a dime, I'd like you to compare the relative strengths of the four forces and then give me something I can understand, like the strong force is as big as a galaxy if the gravitational force is as big as a walnut. You know, something like that. Make those comparisons on the same scale. And I'd like that to be a separate post. And then finally, this is not a post, I'd like you to just do some lifting from our blog. I put up some Coulomb's law problems, and it's about time that we got back into a little bit of classic physics math. So that's your task for the next couple days. Feel free to send me a message on Facebook or send me an email. I'll have access to the internet where I am. Thanks. I miss you guys a lot, and I'll see you on Wednesday.